Hello there, Governor. Top of the morning. Hey, how you doing? We are going to do the second video for the Algebra 2 Common Core June 2017 exam. We are going to cover problems 9 through 16, something like that, 9 through 17. I don't know. We'll stop when things get a little cheeky. Let's get started. Number 9, strict algebra problem. And this is actually a lot easier when you get through all the mumbo jumbo and red tape. A manufacturing company has developed a cost model. Okay, C of X is the cost model. Okay, so let's use highlighters right off the get-go. C of X is the cost model, and it is this thing here. Okay, 0.15x cubed plus 0.01x squared plus 2x plus 120, where x is the number of items sold in thousands. Okay, the sales price can be modeled by S of X. That's the sales price, okay? 30 minus 0.01x. Therefore, okay, if I know cost and sales, therefore revenue, let's go with something a little bit lighter here. Revenue can be modeled by this. Revenue is X times whatever S of X is. Okay, we already have S of X. So in order to get, in order to get revenue, which is R, I need to take X and multiply it times S of X. So I'm going to have X times S of X. Why don't we figure out what that is right now, just to get it out of the way? All right? So R of X equals X times whatever S of X is. This is S of X. That is 30, minus 0.01x. Okay, all I'm going to do is literally distribute the x. So R of x in true equation form without having S of x in it is 30x minus 0.01x squared. This is R of x. And that's important because what they're asking us to do here is the following. Find the company's profit, P of X. How do I do that? I take R of X and I subtract C of X. Okay, so really all you're doing is subtracting two polynomials. There was a lot going on here just to make that happen. So let's take R of X and subtract C of X, shall we? That's what they're asking us to find, our profit. So R of X we already have. It is 30 minus, 30x minus 0.01x squared. Okay? I'm going to subtract C of X, which is this whole thing right here. Okay, let's do this. 0.15x cubed plus 0.01x squared plus 2x plus 120. Now, please, 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 please do not forget, I am not just subtracting the first term, I'm subtracting everything. So I need to distribute this minus sign to everything, which means I'm going to negate everything. Negative 0.15x cubed minus 0.01x squared minus 2x minus 120. I'm combining that with R of x, which is 30x minus 0.01x squared. And now we're just combining like terms. I see one term that has an x cubed in it. It's going to start with negative 0.15x cubed. Okay, it's not 1. Okay, these three all start with that. My second thing is x squared. I have a negative 0.01x squared and a negative 0.0x1 squared. So I should negative 0.02x squared. All right, the only thing that has that next is this right here. That's your answer. It can't be these. Okay, so just for poops and giggles, let's finish this problem off. I have 30x minus 2x, so that's plus 28x. And last but not least, minus 120. Plus 28x minus 120. Perfect. It's just combining polynomials, okay? Don't forget to distribute that negative sign. And what makes this tricky is the polynomials that you're combining, you need to do a little side math here to figure out r of x first, all right? But not too bad. And here we go. We've got multiple graphics and a paragraph to read to answer one multiple choice question, which is fine. I shouldn't be, shouldn't be putting this down, but let's take a look at this. Number 10, data and stats problem. A game spinner is divided into 6 equally sized regions, as shown in the diagram below. Okay? For Miles to win, the spinner must land on the number 6. Okay, so it has to land on this wedge right here. Okay, for Miles to win. All right? Bam. After spinning the spinner 10 times and losing all 10 times, Miles complained that the spinner is unfair. Of course, we're all going to complain. At home, his dad ran 100 simulations of spinning the spinner 10 times. Assuming the probability of winning each spin is 1/6. Obviously, you have 6 numbers here. So, and they're all equal spaces. You have a 1 in 6 chance at landing on any one number. In this case, it's the probability of landing on the number 6. Okay, you have a 1 in 6 shot. That should make sense. So, Miles does this 10 times, doesn't win once. He's like, dude, it's not fair. Come on, that should happen at least once, And, according to the probabilities, it should. But his dad is like, well, okay, this is a math opportunity. Maybe his dad's a math teacher, who knows? And he does a simulation. Spins it 10 times, assuming the probability of winning or landing on 6 is 1/6. Spinning it 10 times. He does that simulation 100 times. Okay? So spinning the spinner 10 times, 100 times. Okay? Here's his results below here. Okay? So this is the probability, the proportion of 6s that come up. All right? So 10% of the spins land on 6s, count here. Okay? 20% of the spins are 6s right here. 30%, because that's where I'm getting these, 30%, 20%, 10%, 40%, 50%, 0%, okay? The proportion of 6s, and that's what Miles needed to win, the 6, all right? So which explanation is appropriate for Miles and his dad to make? So we look at our 4 choices, and they're saying, well, it was likely unfair, not unfair, okay? I hate when they do that. This means that it was fair, okay, and not unfair. This also means, well, that it was fair. Not unfair means fair, okay? Now, right off the bat, what jumps out to me is this column right here. And let me explain something, first of all, before I even get my highlighter. Each one of these boxes, like if I count all those little squares, there are 100 squares in this chart because he ran the simulation 100 times. Each one of those squares, one square represents spinning it 10 times. All right? So what jumps out to me is this right here. 0. These are the number of experiments that did not have any 6s. That happened quite frequently. So I wouldn't say that it's unfair. That's a possible outcome. Okay, that happened several times. So right off the bat, I'm not going to say the spinner was unfair because Miles, my man, ended up here. If I count these squares, okay, if I count all these squares here, there are 19 squares. So 19 times out of the 100 simulations that his dad performed, okay, it says right here, his dad ran 100 simulations. 19 of them ended up not winning at all, just like Miles. That's about 19%. That's, well, not about, that is 19%. Okay. In choice 3 and 4, I see the number 20%. So choice 3 tells me the spinner was likely not unfair, which means it was likely fair, since the number 6 failed to occur in about 20%. That's what this is right here. That is absolutely 100% correct. Sorry, kid, you happen to be one of those 19%ers that didn't win. That kind of sucks, but that is a possibility. Okay, now if he got a 6 on 5 of the 10 rolls, like 50%, that would be unfair because that never happens. Okay, there are no dots there. Okay, but yes, it is a fair spinner because about 20% of the time you won't win. Okay, and 3 is the answer. Whew, off that data and stats and back onto algebra. Which binomial, 1, 2, 3, or 4, is a factor of x to the fourth minus 4x squared minus 4x plus 8? The first thing that pops into my head, and this is kind of a tricky one here, is, all right, well, I will just factor that by grouping because there's 4 terms. And this is where the little trick happens. If I try and factor this by grouping, it is unfactorable. You see, because it doesn't go 3, 2, x to the 1. I'm looking at the exponents, and then there are technically 0 x's back here, okay? The exponents are not off by the same amount. And what does that mean? That means if I try and factor this by grouping, all right, I'll look at the first term. I get x squared. That leaves me x squared minus 4, right? Yeah. All right, if I take out an x squared, which is the biggest common factor I can take out, that leaves me an x squared minus 4. Well, I can't take out, I mean, there's nothing I can take out that would leave me an x squared minus 4. I don't even have x squared here. Let's say, oh, well, can I take out a minus 4? Sure, that would leave me x minus 2. This does not match. Okay, well, what happens if I took out negative 2? Okay, that would leave me 2x minus 4, not x squared. Okay, you can't get them to match. And the whole purpose behind factor by grouping is the 2 things that are factored individually need to match. So you can't do that. And, you know, a lot of my students, they see 4 terms, they're like, oh, factor by grouping. And that's great. I want them to think that. But you should get to the point where when you try to factor, it's unfactorable by grouping. All right? So that leaves me with this word right here. Which one is a factor? If something is a factor, I know that when you divide it in, the remainder is 0. Boom. The remainder is 0. That's how we're going to do this problem. Now, you can use synthetic division because all of these terms are 1x plus or minus something. Okay, I can do that. I could do reverse tabular. Awesome. Okay, but what I'm going to do is I'm going to use the remainder theorem. The remainder theorem does not give me the quotient. It doesn't give me the answer. All it does is give me the remainder. But that's all I care about. Please, 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 if this were a short answer problem, obviously it wouldn't be worded like this, which binomial. It would be different. And they ask you about the remainder being or something being a factor. Don't say there is no remainder. Okay, there is a remainder. It's 0. All right? So what does the remainder theorem tell me? Well, the remainder theorem tells me if I take this factor, x minus 2, this booty cheek, if you will, and I T-bone it, I take the solution, x, and I actually plug it in to all of the x's in the problem. Okay, and whatever it equals is my remainder when I divide it in. All right, I won't know what the quotient is. Okay, so for example, if I had 5, okay, going into the number 32, it goes in 6 times the remainder of 2. The remainder theorem does not give me this, the quotient. It will only give me this. But this is all I care about. Okay, so let's start with choice 1. If I put, okay, first of all, quick review. If I solve this, x would equal 2. If I solve choice 2, x would equal negative 2. Okay, if I did this process, number 2. If I solve this, x would equal a positive 4. And if I solve option 4, x would equal negative 4. So all these x equals, those are the numbers that I'm plugging into my original equation. Let's take this and start with 2. I'm going to plug it in for all these x's. It's 2 to the power of 4 minus 4 times 2 squared minus 4 times 2 plus 8. Okay, all I did was put in a 2 for each one of these x's, okay? Bang, bang, bang. All right, let's do this math. 2 to the power of 4 is 16, minus 4 times 2 squared is 4 is 16, minus 4 times 2 is 8, plus 8. Oh, beautiful. These combine to be 0, minus these combine to be 0. Okay, 0 minus or plus 0. Okay, that's 0. Okay, that's it. These cancel, and these cancel. 0. Awesome. So if it equals 0, that's my remainder. Okay? If the remainder is 0, it's a factor. All right. All right. Algebra. Yes, there's trig involved, but really this is a straight out algebra problem. And I will show you as we do this. Given that sine squared plus cosine squared equals 1, and sine is negative radical 2 over 5, what is a possible value of the cosine of theta? All right. So I'm going to rewrite my equation they give me here. Okay. If sine squared plus cosine squared equals 1, and they give me sine is negative radical 2 over 5, well, I'm just going to plug sine in to solve for cosine. That's it. Simple algebra. Okay. You don't have to figure out like the cosine of degrees. You're not finding out. You're just simply plugging in values and solving. Okay. Now, they don't give me sine squared. They just give me sine. So negative radical 2 over 5 squared plus c squared equals 1. Okay. Well, if I square a fraction, I square the top and the bottom. So I get 2 over 25 plus c squared equals 1. Okay, let's subtract 2 over 25 from both sides. And I end up with c squared equals, I hope you know that 1 is the same thing as 25 over 25. If I have 25 over 25 and I subtract 2 over 25, I end up with 23 over 25. I'm going to continue this over here. Now, if c squared equals 23 over 25, I want cosine. I don't want cosine squared. So the opposites of squaring is square rooting. So I've got c equals plus or minus, don't forget. The square root of a fraction is the same thing as the square root of the top over the square root of the bottom. Well, I know the bottom is 5. I'll just do this. So I have two answers. I have a positive radical 23 over 5 and a negative radical 23 over 5. In this case, one possible answer is positive, square root of 23 over 5. That was not horrible at all. This really, to me, this question tests you on handling radicals and exponents and squaring, handling fractions with radicals and fractions with exponents, okay? When you square a fraction, you square the top and the bottom. When you take the square root of a fraction, you square root the top and the bottom. If you know that, this problem is a layup. It's a gimme. Oh, one of these always pops. You like how I started that? Oh. One of these always pops up on every test. Something where you have to manipulate the exponent. And this is highlighted yellow, the number, so I consider this an exponential or trig. This is clearly an exponential because we have a variable in the exponent. Okay. 13 says, a student studying public policy created a model for population of Detroit, where population decreased by 25% over a decade. That's nice, but we're not going to have to set up the equation with that because they give us the equation in the next sentence. He used the model P equals 714 times 0.75 raised to the variable D, where P is population in thousands and D is decades after 2010. Okay, so right now I'm going to make a little note. My exponent D is decades. That's 10 years, right? It is. All right. Another student, Suzanne, wants to use a model that would predict the population after Y years. Not decades, but years. And this is where the conversion of the exponent is going to happen. So Suzanne's model is best represented by which one of these? All right. I currently have the following. I have the first equation where they only give us Suzanne's name, not this first kid's name. Population equals 714 times 0.75 raised to the d. This is in 10 years. We want it in 1 year. So what I'm going to do is, how do I make my exponent in 1 year? Well, how do I make 10 years into 1 year? Don't I divide it by 10? I do. And when I do to one side, I have to do to the other. But dividing by 10 is the same thing as multiplying by 1/10, isn't it? So I put a 1 here. Okay? So really, in order to make this exponent into 1 year instead of 10 years, there you go. Now that's in 1 year. Okay? My 25% is over 10 years. With that exponent changed to 1/10 d, okay? Now it's 1 year time the exponent. So what I've got to do is I want to take my 1/10 and I want to apply it to my base because I just want my exponent. I just want something like this, and instead of a d, she's going to change that to y, okay? Because it's in years now, okay? So I can really find out like the base, the rate, whatever, when I apply that 1/10 per year, okay? So I need the calculator for this. Turn this on, mine. There you go. I take 0.75 and I raise that to the 1 divided by 10, okay? And I get 0.9716, okay? This here. 0.97164, whatever, and look at that. Bam. Because it's in years, not decades anymore. And there you go. Choice 3. Every test, there seems to be one question where that exponent needs to be changed. Like, you need to rip the number away from the exponent to get the true base and the true change of rate for the new time that you need. Okay. In this case, we had it in decades, which was 10 years. The new time was per 1 year. Okay? Very good. Number 14, another data problem. This is an easy one. Okay? The probability that Gary and Jane have a child with blue eyes is 0.25. So I'm going to say the probability of blue eyes is 0.25. The probability that the child is born with blonde hair, okay, so I'm going to say the probability of blonde hair is 0.5, 50-50 shot. The probability that they have a child with both blue eyes and blonde hair. So the probability of blue eyes and blonde hair is 0.125. All right. Given this information, the events blue eyes and blonde hair are dependent, independent, or mutually exclusive. Okay. Anytime they ask you something like this, it is going to check for independence. It's either independent or not. Okay. Mutually exclusive. I get this question all the time. What does mutually exclusive mean? It's almost not worth explaining to you because it never comes up as an answer. But for the sake of this problem, I will tell you it's not part of the answer. But just to satisfy your curiosity, this means there is no possible way that the events can both happen. Okay, there is no possible way the events can both happen. For example, if I flip a coin, I can either land on heads or I can land on tails. I can't land on heads and tails. That's impossible. So these two events are mutually exclusive. All right? That has never come up on a test that I've ever seen. And watch, it'll come up soon. But I've never seen it. It is always a check for independence. Okay? Obviously, this kid can be born with blonde eyes and blonde hair. Excuse me, did I say blonde eyes? This kid can be born with blue eyes and blonde hair. In fact, there's a 0.125 probability. There's a 12.5% chance he can do that. So yes, both of those events can happen at the same time. So this is not mutually exclusive, okay? So get that right off the board. All right, so let's just check for independence. Here we go. Independence. The easiest way to check for independence, and especially in this case, is that the probability of one event times the probability of another event should equal the probability of both events happening. Meaning, in this case, my check for independence is the probability of blue eyes times the probability of blonde hair. Does that equal the probability of both blue eyes and blonde hair? Okay? If it is equal, then they are independent. If it is not equal, then they are not independent. And dependent is the same thing as not independent. All right, here we go. Blue eyes is 0.25 times blonde hair, which is 0.5. Does that equal both, which is 0.125? If you put this in your calculator, you will get 0.125, and that does equal 0.125. If they are equal, they are independent. Only choice 2. Bam! Mutually exclusive. Crazy. All right, next one. Number 15, trig and exponentials. This is obviously a trig problem. I see sine in an equation and 2 equations. Let's get going. Based on climate data that have been collected in Bar Harbor, Maine, the average monthly temperature in degrees Fahrenheit can be modeled by the equation B of x equals 23.914 sine of 0.508x minus 2.116 plus 55.3. The same governmental agency collected average monthly temperature data for Phoenix, Arizona, and found the temperatures could be modeled by the equation P of x is 20.238 sine of 0.525x minus 2.148 plus 86.729. Which statement cannot be concluded based on this data collection? Okay, look it. 3 of these things are going to be true, which cannot be true. Italics does not mean invisible. Please pay attention to that word. All right? So what I've got to do here is I've got to figure out the average monthly highs and lows, because look at all my answers. The average monthly temperature varies, the variation, okay? Okay, average, the midline average monthly temperature, the maximum average monthly temperature, maximum, okay? The minimum. All right, so I'm going to have to find the average temperature for each one of these, as well as the highs and lows, the mins and maxes. So let's start with Bar Harbor. All right, that means I'm going to be looking at this equation right here. This is the Bar Harbor equation. Okay, in case you did not know, all right, in case you did not know, I forgot highlighting the very last part, which is important, children. Okay, the midline. When I graph something, that's the midline, right? This is my amplitude. My frequency I have to divide out, but that's my amplitude. Let's leave it like that. Okay, my midline, that's the middle of the graph. That's the average. So my average is 55.3. I add and subtract my amplitude, 23.914. If I add it, and if I subtract 23.914, I get my high and my low point, which is the high and low temperature. Okay? That's exactly what I'm going to do here. Let's take this out. There it is. And I'm going to take 55.3. I'm going to add 23.914. I'm going to do the same thing, and I'm going to subtract 23.914. And these are going to be my highs and lows. All right? So my high is going to be 79.214. That is the average high in Bar Harbor, Maine. And the average low is 31.386. Still better than Rochester, New York, I tell you that. Okay, now I've got to do the same thing for Phoenix, Arizona. Okay, so now let me do this for P for Phoenix. Two different colors. Let's move this out of the way. Okay. Now let's look at Phoenix, Arizona. Here's my equation right here. My midline, or the average temperature, is 86.729. I need to add and subtract my amplitude, which is 20.238. That will give me the average high and the average low for Phoenix, Arizona. Man, this is always in the way. So let's start. 86.729 plus 20.238. All right? There seems like a lot. Okay, now I'm going to subtract it. A lot of work to do here. This is taking some time. We are taking our time because we don't want to make a mistake. All right? We don't want to make a mistake, and this is all easy work done in the calculator, and there's a lot of explanation that's going behind it. All right? So let's do this. Let's find out our highs and lows. Our highs, the average high, what is 106.967, and the average low is 66.491. God, it's good stuff. All right, whew. Now we did all that just so we can make a determination of which answers are best. Now remember, 3 of them are true, and 1 is not. Okay, number 1 says the average monthly temperature variation is more in Bar Harbor than Phoenix. Okay, well, the variation means how much does it vary, the average monthly temperature. The average monthly temperature from here to here is about, let's just make an estimate. Well, it's about 48 degrees it varies from high to low. And from here, it varies about 40 degrees. Okay, so yeah, that's true. It varies. The difference between high and low is more for Bar Harbor. Okay, the midline average, this is number 2, for Bar Harbor is lower than the midline average for Phoenix. This is the average for Bar Harbor. This is the average for Phoenix. Yes, the average for Bar Harbor is lower. It's 55, and Phoenix is about 87. Number 3, the maximum average monthly temperature for Bar Harbor is 79. The maximum average monthly temperature for Bar Harbor, this is the max average. Yeah, it's 79. True. So 4 has got to be false, but let's take a look at it. The minimum average temperature for Phoenix is 20. This is the minimum. It is not 20. The amplitude, that's how high and low from the average is 20. But the minimum is not 20. The minimum is 66.9, so about 67. So 4 is your one that's false. There's a lot of work to get to one simple answer. All right, last one. When x is not equal to 0, which expressions are equivalent to 1 divided by the 6th root of x? Okay, that's also saying 1 over x to the 1/6. Okay, top down, bottom out. Okay, so obviously 1 or more of these is the same as these things right here. Well, first of all, right here, if this is over 1, I'm looking at number 3 here, Roman numeral 3. If I flip my negative exponent, I do in fact get 1 over x to the 1/6. That's the same. Look at that. So this is good. Yes, this one's the same. All right. For number 2, if I am dividing bases, common bases, I subtract their exponents, don't I? I do. All right. Well, if I have x, it'll be 1/6 minus 1/3. That's the same thing as saying 1/6 minus 2/6. 1/3 is the same thing as 2/6. And that's x to the negative 1/6, which brings us back to what we started with here. And we already know that that does work, okay, which is 1 over x to the 1/6. Okay, so yes, it's also 2 and 3. So I know 2 and 3 got to be in the answer. This can be an answer. This can be an answer. This only has 2, but not 3. This has 3, but not 2. So all I've got to do is see if 1 is in the answer or not. Okay? 1. If I convert these into bases with rational exponents, that's top down, bottom out, isn't it? 1/6 on top, 1/3 on the bottom. That's exactly what we started with here, which we already know works. It's the same thing. Yes, that works, all 3 of them. 1, 2, and 3. Wow. If you did not know how to manipulate these fractions or these radical exponents right here, I'm going to go ahead and erase all this. Okay? I could do the following in the calculator. Okay? I could do the following in the calculator. I know it's got to be 1 divided by 1/6 root of x. 1 divided by the 6th root of x. If I put this in y1 and graph it, I could put this in y2 and see if it's the same. If it's the same, it's equivalent. It happened to work. Then I could put this in y2. See if that's the same. If the graph is the same, it's equivalent, and it works. Then I could put this one in y2. If the graph is the same, it's equivalent. All 3 graphs would be the same as this graph here, so all 3 are equivalent. You could do that in a calculator. Whew, not too bad. There's a couple of problems that required a lot of work, but it's a lot of simple work, all right? Video 2 is done. I will see you for video 3, which is 17 through 24. Yeah, 17 through 24. Keep on studying. The test is coming up. You are going to knock it out of the park. See ya.